All right, so now we're introducing some new definitions and then proving things using these definitions. So it suffices to prove these results for rings because let me just verify. Rings, second ring, and there's generators. Yeah, because fields are rings, and the statements about fields don't involve anything extra about fields, which is what I was checking. And so once you have it for rings, you just use the fact that rings are fields, and you get everything for free for fields. So let's see here. So let A to 1 and A to 2 be maps from R to R prime. Let them be homomorphisms, ring homomorphisms, which agree on elements of S. So let R and R. Let T be a subset of R, consist of 0, 1, and elements of the form sum from I equals 1 to n s n s and then I1 through si then mi, where Sij is in S. So these are finite sums of finite products of elements in S. This is a ring, and this is something you can verify if you want. Obviously, it contains 0 and 1. The addition and multiplication are the same that they are in R, because all these things are. This is a subring of R, and you can kind of thinking about it, you can see that this would be closed under addition and under multiplication. The addition would be commutative because it would inherit that from the ring, and so yeah, this is a ring. And then you of course get distributivity as well. So you can check that in more detail if you want, but I think it's pretty clear from our construction that this is a ring. R is in, let's see here. So R is in R, and by assumption, let's see here. By assumption, S is a set of S is, let's see here. S is a subset, is a subring generated by S. So capital S is a set of generators on the ring R, which means that R is the intersection of all subrings of R which contain S. And certainly capital T is a subring of R because it's a subset of R and it's a ring, and it certainly contains S, and so capital R is the intersection of all such. Right, all such subrings containing this, and so R must be in T. Because T is one of the subrings over which we are taking the intersection. Does that make sense? Yeah, I guess that's a little weird because you think like, oh, these are subrings of R, but oh, I guess they're all of R because, well, I guess that's sort of the point of it being a generator. So yeah, so this thing we've constructed T is a subring of R, which contains S. And so it contains R. And so R is contained in T. So R is contained in T. If R is 0, which is possible, then eta 1 of 0 is 0 prime, which I will call whatever the 0 element is of R prime. And this is also eta 2 of 0 because these are homomorphisms. And if R equals 1, then similarly eta 1, 1 equals 1 prime equals eta 2, 1. Okay, so we're well on our way to proving that this is that eta is that eta 1 and eta 2 are equal because they agree on 0 and 1. So if instead R equals, say, sum from I equals 1 to n of little si1 through little si mi, then eta 1 of R, you can kind of imagine how this is going to go. We're just going to distribute the etas inside. si1 through si mi, sum from I equals 1 to n, and then we bring the eta inside. We have eta 1 of si1 through eta 1 of si mi, but eta 1 and eta 2 are equal on elements of S, and so we can replace these with eta 2. And this brings us back to eta 2 of, I'll just go straight to eta 2 of R, because you just go backwards the same way we did. Hence, eta 1 equals eta 2. And so there you go. If two ring homomorphisms agree on a set of general... Oh, by the way, for homomorphisms, we used... you really do need it to be a homomorphism of under both addition and multiplication, because we used both of those when we brought eta 1 inside this sum. Because we brought it inside the sum itself using the homomorphismness of addition, and then brought it within this each individual product using the homomorphismness of multiplication. So you really do use everything here, but once you do, there you go. You prove that eta 1 and eta 2 are equal if they agree on a generating set. And so there you go. This completes our proof.